Hello everyone. Today we are going to study about the microscopes. Why are microscopes used? Microscopes are used to see the microorganisms. Now coming into microorganisms are very small. The size of bacteria, fungi, parasites are measured nearly in micrometers. And coming into virus, they are still smaller and they are measured in nanometers. So, seeing these small microorganisms is nearly impossible for a naked eye. So, we need these microscopes. In these microscopes, also, the bacteria, fungi, parasites, these can be measured with light, seen with light microscope. But coming into virus, they are very small, measured in nanometers. So, these need electron microscope. So coming into the general features of microscope. Now there are three main general properties of microscope. Why it is used? Microscope is used for magnification. How organism is magnified? The property of magnification is achieved by use of lens. So microscope use lens for magnification. So the first property is clear. Every microscope use lens for magnification. Second one is resolution. Now, if consider what is resolution, resolution is the ability to differentiate two points as separate entities. What does it mean? When you see through the microorganism, you should be able to differentiate these 2 points. Now, consider these 2 points. Whenever you see from a little far distance, you should be able to see it as two different entities. When you see from far distance, it is like you are seeing a single point over here, but you should be able to differentiate 2 points. So that should be achieved by the microorganism. That is called resolution. Resolution is nothing but the ability to differentiate two organisms as two separate entities. Now, what is the resolution power of human eye? It is zero point 0.2 micromillimeter, and coming into light microscope, it is zero point 0.2 micrometer. Coming into electron microscope, the resolution power is nearly 0.2 to 0.5 nanometer. This resolution depends on refractive index. Now consider water and air, no, oil and air. Now oil has higher refractive index. So you might have heard that you use oil for oil immersion where the magnification is very high, because resolution depends on refractive index. So oil has more refractive index, so more resolution. Next, coming into contrast. Now, contrast, you can't see a white organism in a white background. So, if this is a white background, you can see it when you have written in the black color, this one. So, you need a proper dye so that you can see the microorganism. So, contrast is required. So, these are the three main properties: magnification, resolution, and contrast. Now we will discuss about the microscopes. The first basic microscope which we use is the light microscope, which we use in even in our labs. So light microscope, which is also called as bright field microscope. This is also called as bright field microscope. So light microscope, the other name is bright field microscope. What is its role? It forms a dark image. Remember, it forms a dark image against the bright background. So it is called bright field microscope. So next, coming into the light source. What is the light source for this light microscope? That is the transmitted light. You use the transmitted light. See, how does it work? See, this is the light microscope, or bright field microscope. So in this microscope, here is the source of light. So from here, from this light source, the light passes like this. So this light goes up. So here is the condenser. What is the role of a condenser? Condenser focuses the cone of light into the specimen. This is a condenser which focuses the cone of light into the specimen. So this condenser has a movable part here. This is called iris or diaphragm. So what is the role of iris or diaphragm? It regulates, it controls the amount of light which passes here. So how much light should pass, you can use this one to control the amount of light that passes into the specimen. Where is the specimen located? See, this is the stage. Stage is where the hero lies. Who is the hero? Is the specimen. Here you put the specimen. So this is the slide, this is the specimen, and this is the stage. So upon stage, so light passes from here, from the light source into the condenser. In condenser focuses it into the specimen. From the here the light is gathered by the lens. Which is the lens? This is the objective lens. There are many objective lens which we will learn further. These are the objective lens. These can be turned by a revolving nose piece. When you turn this one, you can like turn the objective lens into different pass. Next is the ocular lens. Ocular lens is seen where ocular lens is also called as eyepiece. So this ocular lens, these are the ocular lens. Ocular lens is also called as eyepiece. So this is used to magnify the image organism still more further. So coming into eyepiece lens has a magnification power of 10x. Whatever eyepiece it is, this has a lens of 10x. Here you can see there are two eyepieces. So this is called as binocular microscope also, because there are two eyepiece over here. Normally you can even have a single eyepiece also. So eyepiece has a magnification of 10x. Next, coming into the objective lens. The objective lens, there are, here you can see, right, this is the objective lens. There are nearly 3 to 4 objective lens. The first one is the scanner, then it's the low power, then high power, then oil immersion. Now first coming into scanner. Scanner has a magnification of 4x. Coming into low power has a magnification of 10x, high power has a magnification of 40x, and oil immersion has a magnification of 100x. Now, how do you calculate the total magnification? This is how the MCQ questions will come. What is the total magnification of a low power microscope? Like with the objective of low power, you should know. So, see, the objective lens magnification for the scanner is 4x. For low power is 10x, for high power is 40x, and oil immersion is 100x. Eyepiece is always same, it is always 10x. So multiply this into this. So 4x into 10x, it is 40x. So total magnification is 40x. For low power it is 100, for high power is 400, and for oil immersion it is 1000. Next is the numerical aperture, which is not that important. Still, I'll explain it. The numerical aperture is nothing but the angle by which the light falls on the slide and gets reflected. It is very simple. See, this is the objective lens. Whatever you see over here, this one. So this is the objective lens, and this is the slide where the specimen is. So there is a cone of light like this, right? So what is numerical aperture? It is by, should know the formula. It is n sine theta. What is n? See, you have the formula here. Here, what is n? N is nothing but the refractive index. Okay, then what is theta? Theta is the half angle between the object and the lens. So this small angle what you see, this is called as theta. So you calculate by the angle and the refractive index. Normally if it is air, the refractive index is 1, so you put 1 into sine theta, or if it is oil, 1.5 into sine theta. Like that you calculate. See, the one main important thing is that magnification increases as the numerical aperture increases. So whenever the angle increases, see, whenever you turn the objective, when the lens comes very near to the slide, the angle theta increases. You can see the theta. From here to here, the angle increases. When the angle increases, the numerical aperture increases. So as the magnification increases, the numerical aperture increases. And another important MC question is the total magnification offered by a light microscope. What is the total magnification offered by a light microscope? It is 1000x. Next, coming into the second microscope, that is the dark field microscope. Here the light source which you have to remember is the reflected light. And next, the features are similar to whatever you have learned in the light microscope. Here the thing is that it's here you use dark background, and the object appears very bright. See, these are the objects which are very bright in the dark background. So coming into the microscopic structure, this is the how the microscope is. It is very similar to light microscope. Here the condenser, only difference is the condenser. There is a difference in the condenser. How is the condenser? You can see the central annular hollow area, so here light cannot pass. And there is, sorry, central opaque disk. This is the central opaque disk, and side there is a peripheral gap. So in this gap the light can pass. In center light can't pass, only in these gaps the light can pass. The gap is called annular hollow area, and the centrally there is the opaque disk. So the condenser, the difference in the condenser is centrally there is opaque disk, and in the side, in the periphery, there is the annular hollow area where the light can pass. So this is how the light passes. From here the light passes into the specimen. So from there the objective will take only the deflected light rays. The unreflected light rays go away, so the background appears dark. So this is the reason why the background is dark, because the unreflected light rays move away and not into the objective. Only the light which falls on the specimen enters the objective. Next, coming into where this is used, dark field microscope is used to see the thin structures, mainly the flagella, spirochetes. Here we use the dark field microscope. Next, coming into the fluorescent microscope. The fluorescent microscope, the light source which you have to remember is the UV light. So what happens here? Here you have this light source. You can see the light here. From here the light comes. That is the UV light. The UV light then passes through the excitation filter. What does this do? From the light source, it will take the shorter wavelength light rays, and it will only allow shorter wavelength light rays to pass through the excitation filter. So that will come like this. All the shorter wavelength will be filtered, and shorter wavelength light rays will come this side. So from there will be the dichromatic mirror. This is dichromatic mirror. So whenever this comes here, it gets reflected into the specimen. And one more feature what you have to remember is the specimen is not just a normal specimen which is kept. This is mixed with the dye. That is the fluorescent dye. So you have to remember few dyes, like, which is important. The few dyes for TB. For TB the dye is auramine or rhodamine, and for malaria it is acridine orange. For fungus is calcofluor white, and for fluocyto, this is used in pathology actually. You use FITC, that is fluoroisothiocyanate. So this comes, then this excites. What happens here? Whenever short wavelength comes, shorter wavelength light is converted into longer wavelength light, which is in the visible region. So these are visible lights which then directly pass above and which you can see. But before that there is a barrier filter that is used to protect your eyes from the UV rays. If ever UV rays comes, it will protect your eyes so that your eyes are not damaged. So the main property over here is that the shorter wavelength light is converted into longer wavelength light, that is a visible light. Then here that dichroic mirror is used. Then not all specimen should be we should add the dye. Like some specimen have the autofluorescence, like the cyclospora and isospora. They show the property of fluorescence without the dye. And even other than this is micrologically important, but other than that, we even know that formalin and NADPH also show the property of autofluorescence. So NADPH is used in the fluorescent spot test in G6PD deficiency. And coming into formalin, the one of the applied aspect is that during skin biopsy, you don't put the skin biopsy specimen in formalin and give for whenever you want to do immunofluorescence. Why? Because when you put in formalin, even formalin will show its autofluorescence, so you can't do the test. So you put that skin biopsy, while doing skin biopsy you put in the normal saline and not in the formalin. Next is the phase constant microscope. You need not study in detail. You have to remember one thing, that here two extra things are used. What is that? That is the annular diaphragm in the front of the condenser. Here near the condenser, this is condenser. In front of the condenser, you use the annular diaphragm. This is how the annular diaphragm looks like. There is only a small circular gap over here where the light can pass, and another up above. See, it also has an annular face plate at the top. This is objective, right? Above objective there is the annular face plate at the top. So this is done when there is different refractive index. Now consider this is the cell has nucleus, mitochondria, all endoplasmic reticulum, all ribosomes, all other structures will be there. All the structures will be having different refractive index. So different refractive index have different phases. So there is change in the amplitude of light. So you can see the image. That is how the phase constant microscope works. Next, coming into the electron microscope. Electron microscope was invented by Ernst Ruska. We here, instead of light rays, here there is no light source. Here you use the beam of electron. So here the electron gun will be there. So this will bombard all the like very high velocity electrons will come from here, and it will fall on the specimen. So here, instead of air, vacuum is used. Why vacuum is used? Because when the electron comes with the higher velocity, it should not bombard with all the air molecules, air particles. So instead of air, you use vacuum. So vacuum is used so that nothing is obstructing its pathway. This is the electron microscope. So it will go, then it will scatter inside. So the electrons go from here, then the specimen scatters the electron passing through it, and then the electron beam is focused by the magnetic lenses over here. Then you will get the image. That is how the electron microscope works. Next, coming into the difference between the light microscope and the electron microscope. The first is the resolution, which was our initial point. The resolution of light microscope was 0.2 micrometer, and resolution of electron microscope is 0.5 nanometer. What is the medium used? I have said now. For electron microscope, you use vacuum, but for light microscope, it was air only. And what is the source? Source is the transmitted light. For light microscope, for this electron microscope, you use electron. And for light microscope, which you use in your labs also, you use the slide is the glass slide. But for electron microscope, you use the metallic slide, which is made up of copper. Next, fixation. Fixation is done in light microscope by 10% neutral buffered formalin. But in electron microscope, it is 2 to 2.5 glutaraldehyde. And embedding is done in resin for electron microscope, and for light microscope it is the paraffin wax. Next, coming into electron microscope types. What are the types of electron microscope? That is SEM and TEM. What is SEM? SEM is nothing but scanning electron microscope. And what is TEM? TEM is transmission electron microscope. Coming into the features of SEM and TEM. The principle is that SEM is where the electrons are scattered. So electrons are scattered, electrons are used, and here the transmitted electrons are used. So whenever you come into details, you will see the internal details in TEM and surface details in SEM. And view, more sample is viewed in lesser time, and here less sample is viewed in the same time. Then dimensionally, like you get 3D image, and here you get the 2D image. This is the whole thing about the microscopes. So thank you.